So thanks, Vonu. I'm probably the only, well, I am actually the only outside speaker here today, so I guess I can probably take it a little bit further than what some of the others have, because my funding is not dependent on what I say. So I do actually have I put this up just to show that I do have actually some Scottish connections. My first name's Glenn. Oh, actually, my first name's Donald, which even makes it closer than if Glenn's not good enough. But my great-grandfather, despite being born in London, saw the light and came north, and was a lamplighter in Edinburgh in the 1901 census. And my other connection, of course, apart from the first two, is I co-authored a book with Vonu before she actually moved over to, while she was moving over to Glasgow, which made it doubly difficult to write the book, and it took a lot longer. And it took a lot longer than it should have to complete. So that's an advertisement. Please go and buy the book. And so going back to the other point there with my great grandfather, I was wondering if you could somehow time travel into today. So he hopped in the TARDIS, and there actually is one down in Glasgow. I happened to come across one. A blue telephone box. So somehow he popped out of there. What would he actually see? And if you took away the cars and that, which, I mean, okay, he'd probably notice a lot less horse droppings, which is probably a good thing, because that was a big deal back then, and one reason why people were happy for having motorised transport. But what he would notice is these people walking around with these damn things. This is the way they walk. They're not looking ahead, they're looking down. I mean, the fabric of the city hasn't changed. I mean, some people have two, right? I mean, I've got two of them, you know, here we go. Some people have more of them. And that's really the big difference. It's the connectivity that he has, not just with the things around him, but with with the whole world. Use them for navigation, you use them to keep in contact with your friends. And that's something which I think the Urban Big Data Centre has to really take and use to get the most out of. What people are doing on these things, how to track them, know what they're doing. So the other thing I can do is give an advert for my research centre. NICTA, National ICT Australia, we're Australia's largest information communications technology research centre. We have 5 research labs, a couple in Sydney, Canberra, Brisbane and Melbourne. We have around 700 staff, of which about half are PhD students. We have 22 university partners. We appropriate about 80 million Australian dollars, so that's 40 million pounds from federal and state governments. We earn about 20 to 25 from doing contract research and various other grant schemes. We can't apply for regular research grants because they're already giving us money, so it's kind of double dipping. I should point out though, for that $100 million notional investment, a well-known accounting firm, consultancy, has valued us as doing $3 billion impact to the GDP, which is a pretty good return on investment, if you ask me. We've had 14 spin-outs in our life. I should say we're also founded in 2002, so we haven't been around that long. We've had 14 spin-outs. Right at the moment, we're spinning a company out every 3 months. We sold a company about probably a couple of months ago now for 10 million Australian dollars. And we are a not-for-profit. We produce, 600 research papers a year, so 1 research paper per research, and we've got about 100 patents on the go in the portfolio. So we have 2 really simple key performance indicators: research excellence and wealth creation. So wealth creation doesn't mean my next suit's going to be Armani. It means that there could be a GDP event, right? So if we work on traffic congestion and reduce that, there is a GDP event. And if anyone's got an Android phone, you're actually running software developed by NICTA. So the microkernel that's sitting in there has been shipped on. It's more than that. Now it's close to 2 billion Android phones. So if you've got one of those, you're running software developed in our labs. So that brings me up to really the main focus of the talk, which is about what we're going to do in cities and what NICTA does in cities. So I'm going to give you a whole bunch of examples, but first of all I'm going to tell you about 2 technologies. And as I said, research excellence, we have research groups in machine learning and optimization. The scale of the group is about 100 people per group. Optimization group, as I say, both of these are arguably top 5. But we have the 2 most highly cited scientists leading the optimization group. And we have had people like Alex Smoller and that working with our machine, and one of the developers of Support Vector Machines. So for those of you who aren't really au fait with the sort of technology, machine learning is really methods and techniques for pattern recognition. So you can show the algorithm or show the systems examples of a particular type, and then hopefully when you show it other data in the future, it can make inferences about what that data is like. That's pattern recognition. You can also do it with continuous variables, and it's regression. There's also, so that's supervised machine learning. There's unsupervised machine learning, which is clustering. So you give it a whole bunch of data and you say, find me the bits that lie near each other, cluster them together. And what you can do with this is build these data-driven models. And I know a lot of social scientists don't like data-driven models because there's no causation. But the work, for a lot of the work and the work that we're doing, causation's not that important. And you'll see why as I go on. And again, optimization is a bunch of methods for making sure that things are operating at their sweet spot. And there's a lot of work that's been done over the last decade which really has speeded up this optimization process enormously. So we do have an enormous amount of data. You always, every talk, and I'm surprised that no one has realized, actually Vonu said at the beginning, I should say that last week, 99% of the world's data was created. Maybe it was.
I took out the slide.
Okay. Well, I know you've said it in the past. Yes. Yeah, everyone says that. So we all have to have a slide like that. Whether it's 90% or 100 or 85%, doesn't matter. There's a lot of data. Most of it is noise. We have to look through it to understand what's going on there. What are we going to do with it? Do we store it? Good point. More data doesn't make better data. And there's an interesting example there. 400 million taxi records collected in New York City. People go and analyse these to death. We use 400 million taxi records to work out the origin and destination of passengers, but nobody's ever taken the data set down by a factor of 10 and see if they can get the same numbers out, and I'm sure you can. You don't need all the data all the time. Computers have got a lot faster over the last, this is from over the last 20 years. A lot faster, and it's going to continue to grow. Something will happen. I mean, there's always been this notion that you're going to hit the physical quantum limit of the speed of computers. They just put a few more cores in there now and bolt them together, and you're just keeping going up at great rates. What will happen probably in the next 20 years, there'll be usable quantum computers, which will make the whole thing, which will be a complete game changer, and all these speed limits just go to pot. Algorithms as well. As I said, algorithms are also getting faster. Cplex was a company that was bought by iLog, which had now been bought by IBM. It's basically a collection of algorithms for doing optimization. At every version change, there's been speed up. The algorithm has speeded up by 30,000 times in however many versions there are there. Multiply that by the 1,000-fold increase of computer power, and you've now got a 1 billion times speed up of how fast you can do your optimizations and how big the systems can be that you can optimize. This gives you this gives you city scale possibilities for optimization. So what I'm going to do is go through a few applications, a few projects that we've worked on in NICTA. I'm not going to talk about the open source telepresence, but I will talk about the majority of the other things that we have up there, and I have some videos and things, so please enjoy. So one thing we've worked on a lot is smart infrastructure maintenance. We have instrumented the Harbour Bridge. The Harbour Bridge was built in 1932. It had an 80-year lifespan. It should have fallen down 2 years ago. I mean, if you can add, right? I mean, it's the world's widest bridge. Bradfield designed it really, it's a really good design. The right-hand, this is looking in from the eastern side. On the eastern side here, actually, I'll take a step back. Sydney had the largest tram network in the world until 1961, when the state government, in its wisdom, burnt all the rolling stock because diesel buses were better. Now, ironically, they're building light rail, better known as trams, back again, and that's led to them giving us some money, so it's okay with me. So the thing about this is what happened on this lane here, the supports were along the tram lines. But when the buses came along, they operate offset to the tram lines. And there's a nice cantilever. And bits of it fall off. I didn't say that, and he's not going to record it. So bits of it fall off. So the bridge owner, the Roads and Maritime Services, came to us and said, can you help us understand how this thing is going to fail? So we've instrumented the bridge with a large number of basically accelerometers, 3-axis accelerometers, which you can self-calibrate, work out where down is, because gravity happens to be a constant acceleration of 9.8. I'm a physicist, 9.8 meters per second squared down. And in fact, I am a physicist by training. And when the beloved buses go over that lane, they excite vibrations in the structure. And by using, as I say, quite relatively cheap data acquisition systems, all wired together, they could be wireless. They're wired for robustness. Again, it was a mandate by the owner of the bridge that they want to know when this thing's going to fall down. Pretty important. And then by looking at how the accelerometers operate at various points, and by actually inducing failures, if you like, in the bridge structure, you can cluster together events, vibration events, which look the same. And from those events, you can construct a health score for each of the joints, which you can then provide to the bridge engineer to tell him which joint he should go and look at before something catastrophic happens. The bridge isn't going to fall down, just a 15-kilo chunk of concrete falls off. Not very good if you're underneath it. So this is ongoing work. We have about 50 nodes. The plan is to go out to around 1,000 by the end of the year. Another interesting piece of work. Again, it's all urban work. It's all city related, not necessarily data. However, we are collecting the data on the bridge. That data is stored. It's big data. Lots of data. It's sub-second sampling. Another interesting bit of work we're doing is in infrastructure maintenance, but smart pipes. Australia has 140,000 kilometres of 180 millimetre water mains or larger. They break about 1,000 times a year. They cost $1.4 billion to repair. Most of those costs are not in the repair as such. It's really because it floods a basement and everyone's Mercedes and Ferraris get flooded and the insurance companies have to pay out. So again, by collecting various bits of data that the water authorities have on the pipes, flow rates, pressures, soil types, that sort of thing, can you construct a model to predict where the pipes are likely to fail in the future? Again, it's not to say that pipe over there is definitely going to break next week. It's to say within the next 2 years, there's an 80% chance that pipe will fail. So they can do preventative maintenance rather than waiting for it to break and fixing it. It's much cheaper. Compared to the previous methods that water authorities use all over the world, the methods that are used at the moment are pretty much toss a coin and hope. We can do a hell of a lot better than any of the current methods that are being used. And again, what with all these machine learning techniques, what you do is you have a whole bunch of data, you train it on a certain amount of data, and then you compare to what actually happened with some of the other data you've got left. And as you can see, we did a pretty good, if you have a look at the red points, they're all in pretty much the areas that we picked up that they should have gone and looked at. So, as I say, I should have put this slide up perhaps first, but we took various things, just used various methods and then went out and did it. But the point to make here is we're not worried about why the pipes are breaking. So there's no causation there. All we're doing is taking the data and saying, can you tell us, or can the data tell us where pipes are likely to fail in the future? We do have huge issues. We are trying to work with corrosion scientists. They do not like us very much because they don't understand what we do. And that's a hard sell. It's a very hard sell. How do you, and it goes for also for the transport world as well, because it's not classical modelling. There's no micro simulation, it's just let the data tell you what's going on. So moving to probably my favourite topic is traffic. We all know cities are crowded. Australia is the most urbanised country in the world. Most people live very close to the coast, and if you look at the top, sort of from Brisbane down to Melbourne, you have more than half the population of the country. The population size is 22 million. You have about 12 million living in Brisbane and the southeast Queensland, Sydney and Melbourne. Very, very heavily concentrated. Congestion costs us a lot. These figures are from the Bureau of Transport and Regional Economics, a government department, federal government department, $9.6 billion in 2010, set to double by 2020 unless we do something about it. The 1 to 2% of GDP figure here holds for the vast majority of developed countries. So if you go and you look at the GDP, you can work out what your congestion costs are by just taking 1 or 2%. The other issue, of course, is safety. The UK is actually one of the safest countries for driving in the world. I mean, you have to go further north to Scandinavia to get lower. Australia is pretty good. However, we still have 1,600 fatalities per year, cost $10 billion, however you value that. I mean, one fatality is probably worth $10 billion to the people who are involved. So, the crash rate is reducing through the introduction of all sorts of in-vehicle technologies, forward collision warning radars, airbags, seat belts, all that sort of thing. But really, there's not much you can do without going further and integrating the infrastructure and vehicle-to-vehicle communication, that sort of thing, which I'm not going to really talk about today. Also, costs a lot. Congestion costs a lot. 17% of transport emissions come from greenhouse. 17% of all transport greenhouse emissions come from stopped traffic. Emissions double from stationary vehicles as from moving vehicles. So you really want to keep the traffic flowing. But the good thing about transportation is, of course, efficiency, safety and sustainability go hand in hand. If you think about a dual carriageway, you can kind of see that. The traffic's flowing well, it's pretty safe, and the cars are running pretty much at their engine sweet spot. So we have a whole range of activities in the sort of data space for transport. And I should say, it's not just big data. It's data. I mean, the concept of big data is a moving target. When I started at university back in 1983, they had a dishwasher-sized, 200 megabyte disk drive attached to the VAX computer. Now you can sort of get a 128 gigabyte micro SD card. So the big data has completely changed over that time period. So in another 10 years, big data is not going to be big data as we see it today. So the big data is going to be bigger or something. It's going to be different. So I'll go through a few little demonstrations and hopefully this will start up. Yep. Sorry, let me go back. Okay. Will it run without me doing anything now? No, probably not. Where are we? Okay. So this is the city of Perth. The city of Perth is building, widening motorways. And we were asked to have a look and see what would happen if a technology called ramp metering is deployed on the ramps. Now, because this is what the freeway is going to do in the future, we needed to do predictions of origin destination, and based on old surveys, but also based on data that we could take from loops. So does everybody know what ramp metering is? Who doesn't know what ramp, do they use ramp meters in the UK? Yes. Okay, That's good. So everybody, well, ramp means basically signals on the on-ramp of a freeway, right, of a motorway. And you balance the outflow with the inflow on the motorway. So congestion on a motorway on a freeway is caused not because of too much traffic coming in, it's because you can't get the traffic out at the other end. So ramp metering tries to balance those two out by timing or allowing only a certain number of vehicles onto the ramps. So basically by doing ramp metering, we showed that we could increase the capacity by 41%. And if they really need to do this because of the projected growth in the population. And this is the important thing. But the other thing this shows is another field which is somehow linked with big data is visualization. This is a sexy visualization. So, you know, that's another thing for people who are working in this space. You should think about doing nice visualizations. They may not contain any useful information, but they are good for your funders. So transport social media integration. This is a bit of work that we did again with Vic Roads, the Victorian Roads Agency, looking at using Twitter to predict or actually find incidents in the Twitter stream. And the interesting thing about this is we only use geolocated tweets initially, and it turns out that for non-crash type incidents, so breakdown, broken alternator, whatever, people don't ring up and report this because there's nothing happened. So we can give up to 3-hour head start to the Transport Management Centre, which means they can get their crews out there and clear the incident before it becomes, you know, basically, you know, the road to ruin. Now the thing about a lot of the Twitter work, and again, it's something which has to be considered. If you're looking for geolocated tweets, it's only a few percent of tweets that are geolocated. You then have to look for things like, there's a crash near McDonald's up the road. So it comes back to natural language processing. And that's actually way harder than processing the Twitter stream. I mean, natural language processing is a machine learning problem that probably isn't completely solved. So you've got these errors that come into the system, but we you know, as I say, we can produce a lot of good information. The Sydney CBD here, again, the Transport Authority of New South Wales, in their wisdom, are putting back light rail now, despite having pulled it all out in 1961 and burnt the rolling stock. And they came to us and they said, can you please tell us what's going to happen to the roads during the construction phase? Well, we could say, yes, it's going to go to hell, but we have to provide some reasoning for that. Now, the problem, one of the things about machine learning is, if you haven't seen it before, you really can't predict what's going to happen. It kind of doesn't work that way. So the street which runs down the middle here is called George Street. And I mean, every British-inspired city in the world has a George Street. And part of this street is going to be closed permanently when the tram runs. So this is north-south. So the Harbour Bridge is up here, and the University of Sydney is kind of over here. For those of you who know the city. So basically what we had to do was find some data, find some training data that included closures of this street. And it turns out they close it for football parades when teams win, and they also close it for Anzac Day marches, which is kind of like Remembrance Day or what's the November 11, whatever it's called here. Again, what we did was we took data from loops, so these are inductive loops that are mounted in the road, that under the road surface that count cars, and tried to predict, using that data, what will happen, and then look at what happens beyond. So basically, you look at it during a closure, and then you try to predict what's going to happen after the closure, how quickly it builds up, and we get pretty good results. So in fact, with this, they're now funding, the Roads and Maritime are now funding further work to extend this outside for the rest of the route of the tram, which is much further out. Yeah. Okay, I have to be quick now. The schedule I've got is completely weird then. Well, my watch is completely out. We also work in public transport, hub and spoke transport. This is using taxis to replace buses other than on point-to-point routes during off-peak services. And in fact, this is a really good system, and we've done this in simulation. The really good thing about this is not only do you make it easier for the passengers, you also make it better for the bus drivers, because you only have the 2 bus drivers who actually want to drive on the weekend. The rest of them can stay home. So you've got a sort of a social problem solved as well. Of course, if it becomes too popular, it could be a victim of its own success. That's yet to be proven. This will go into trial early next year. It's just in negotiation now. This is an evacuation, optimisation of an evacuation. This is a flood from the main dam that supplies Sydney, flooding down into the valley. And basically here, these are cars moving out, taking people out. But you can see that because it takes a topography of the ground into account, there's little pockets of people who get left behind and don't move until you probably wouldn't. I don't think a human looking at this would predict this sort of evacuation plan. This is a rather interesting one as well. It'll start up in a moment. Again, using real data in this case. If that doesn't work, I'll go back. Hold on. Yeah, okay, it didn't start. It will start in a sec. So this is the main container port in Sydney, the railhead. Only 14% of containers go into the port by train. They want to double that. This is an intermodal yard called Enfield, at a place called Enfield. Again, every English-speaking city in the world has a place called Enfield. This track is duplicate track, except for about a 3-kilometre section in the middle. And the standard view was what was going to be the bottleneck here was in fact this single track, because the trains have to wait. But in fact, by looking at actual real data and optimising it, what was actually happening, the load rates at the stevedores are too low, the trains don't go in full. Companies actually own slots on the rail, and they buy the slots and don't allocate them for commercial reasons, without doing anything. This will completely, if done properly, if everything is done in an optimal way, there is no requirement to build this rail, to duplicate the length of rail line here, the 3.2 kilometres, till 2030. It saves the government $200 million. That's a pretty good saving. So, to finish up, what are the messages? What do I want you to get out of this? Well, clearly we can now model large-scale systems. Computers have speeded up enough and all the techniques. We can optimise them, we can predict about it, we can make predictions. Now, what we have to do, and the Urban Big Data Centre in particular, is go out and collect data, instrument them, and then make them more productive and better socially and environmentally. And that's a real challenge for your centre.
Yeah, I wish speakers said that. Yeah, so scary.
So I'm happy to...
All right. Thank you, Glenn. Questions for Glenn?
Hi. Thank you very much. Very interesting. You emphasised the contrast between social science, theory-driven research and the machine learning a-theoretical approach. The data you feed into your machine learning models is clearly based on theory. I mean, it's not a-theoretical in that sense.
No, it's real theory. It's people or things.
But
yes.
the data you fed into your pipe breakdown model was about soil conditions and pressure
Sure.
of materials. You have theories about why these things matter rather than everything else. So are you overstating the kind of
Possibly. Maybe it's just a feeling I get when I talk to my friends who are planners. And social sciences.
Is the advance there, therefore, that comes as much from theory as from, isn't the company more volume of data?
No, I think, yes, you're right. You don't need more data. You just need better ways of analysing it. I think that's right. Yeah.
Just following up on that point, I suppose one of the sort of standard criticisms about big data and lack of understanding of what's going on is an analogy with the global financial crisis. Essentially, no one actually knows what's going on, all sorts of algorithms operating, the whole thing falling apart. Is this a sort of fundamentally different from that sort of world? Second part of the question, you sort of rather dismissive, I think, about the visualisation. It seems to me that visualisation actually could be something very useful to explain about what was going on in
Look, I agree with you about the visualisation, but I mean, a lot of people do regard the visualisations as just as toys, and in fact, they're not. You're right. Certainly, when the number of variables you've got, the amount of data you've got coming in, and the systems are complex, the only way to make it understandable, even to the scientists who or even to the researchers, is through a visualization and not looking at rows of numbers in a spreadsheet. And I agree absolutely. And I think with the first part, I'm still. Yeah, I mean the whole issue of causation is still vexed, and I think, but one aspect that hasn't been looked at a lot and is something that we're kind of thinking about as well, and it's something maybe more general, is if you actually have some data collected from the real world and you have a simulation model of the real world and you have data gaps in your real world model that you need, in your real world data, but you need to drive a data-driven model for some reason, can you in fact use the simulation to fill in the gaps? And my thought on that is, provided you do the right sort of machine learning and you can handle the uncertainties that are going to be different between the two, you probably can. So I think that goes, it's really a mixture. I think the mixture of all these things is what's going to win in the end. I don't think there's no one size fits all.
Have you or anybody else done any pedestrian flow modeling?
No, we haven't, but it certainly is done. In fact, if you're interested in some, go on, sorry, there is.
Yeah.
But if you're interested in some very interesting data, the City of Melbourne has pedestrian counters around the city, and you can actually grab the data from those particular counters, and they're quite fascinating to look at. I mean, we've looked at them but haven't done anything with them as yet.
Anything else? Yes.
Yes.
That's one question. I mean, big infrastructure planning in this country anyway is done really on the basis of, I suppose, historical data about traffic flows and also economic models, which don't easily fuse together. And some of this information is quite historic. It's by its nature 4 or 5 years out of date by the time it's getting applied to the problem. And also it tends to be done discreetly, so that each project is looked at separately.
Absolutely.
So you don't get the interflow between the two. And as a result, I don't think we get a very good decision-making process in, kind of rating projects against each other or looking at the economic benefits. What we're now getting, I think, Glasgow's city is part of this, is people getting offered infrastructure money on the basis of social return. The big social return is employment in Glasgow's case, and I guess in the other city deals. Is there a way in which using sensor data, real-time data, etc., is actually going to make this much more effective than the methods we've got at the minute, and what are the key things in taking that forward?
So that's a very, very interesting question, because again, if I think just about traffic, right, there's a whole hierarchy of models. There's the sort of micro simulation model, which looks at how all the cars move around. Then above that, there's kind of the flow model, where the flows are treated as water flow on the road, and above that you could imagine that there's an economic model. So the levers that get pulled at the top, how do they go down and influence what the driver does? And I think and what are the interconnections between those models? Is there more than one model, or can you somehow have this single model that does? And this gets back to what Sir Alan was saying, right? That how do you have all these multi-scales? Is it one model? Is it more than one model? And ultimately it's all about productivity. And it's all about extending the life of infrastructure, which is increasing productivity. Comparing the price, well, comparing the benefits of infrastructure is very hard. And I mean, certainly in transportation, they use a lot of equilibrium modelling. And really, observationally, equilibrium models don't hold for traffic. Traffic is never really in an equilibrium state. I mean, that's really a nicety. And actually, the one thing that Sir Alan didn't say was that I think was it Box who said all models are wrong, but some of them are useful. And that's exactly, it's horses for courses. So if you can find a model that will actually take some real projects, apply the methodologies, and see if the rankings worked, and then you could apply those methodologies further on. And I think the data will help. And the data will help because what we did with, say, for example, the motorway, was we had household travel survey information which gave origin destination, which is clearly wrong because it's taken some time ago. But you can augment that with traffic counts, pedestrian counts to get OD, and then you get a much better estimate of what you're going to do. So the input to your model will be a lot better from the data, using data analytics to actually seed the model that makes the modelers happy because it's a model they understand and not some sort of random black box that just spits out congestion. There's actually some real sort of physics in there. So I think I think you will get more out of it. You just need to do it right.
Anybody else with questions? Otherwise, thanks to Glenn and that's